So take a look at B. It says f of x is a polynomial function, not randomly chosen words, and selected values of f of x are stated, misspelling, stated below. What is the minimum number of times that f of x equals 2? Justify your answer. So I want you to think about this for a second. It doesn't ask what the answer is, does it? It doesn't say what's the solution. It says, what? Well, it does say justify your answer, but as far as like the meat of the question, as far as like, now your response needs to be backed up by a justification. I agree. But what response are they looking for? Are they looking for x equals 4? What are they looking for, Matt?
Just asking for the minimum number of times.
Yeah, like how many answers are there, right? It's not asking what they are, it's just asking how many there could be. Do you see how this is a little bit of a twist on a question? I mean, you're not used to this, are you? Like in pre-calc and algebra 2, it was always, what's x? Solve for x. Find x, right? Find the zeros. Find the x-intercepts. That's not what this is asking for at all. This is just saying, hey, we don't really want you to solve it, and you really can't, because did I even give you a function to solve? I didn't. I just gave you this table of values with inputs and outputs and inputs and outputs and all that stuff. And all I want to know is how many answers could there be? Not what are they, but how many could there be? Do you follow? Do you see how this is a little bit different? And so let's think this through logically. What kinds of things might you need to know in order to respond to this? How many times? What is the minimum number of times could f of x equal 2? What hints or clues might you be looking for? What do you think, Johnny? Use the IVT. Okay, I agree. If we're going to use the IVT, there's some certain things we need to consider. What do you think, Zach? What's one of those things?
Values or f of x values both below and above 2.
Y values above 2, y values below 2. Fair enough. Does that make sense? Because if you are above 2, and then later on you're below 2, maybe you went through 2 to get there. Make sense? Remember the doorway example? Or was it no, it was Catherine's bag, right? So, Jake, what did you want to add?
We need to make sure that the function is continuous.
Yeah, because Zach's reasoning actually makes no sense if the function's not continuous, right? So what do you think, Hannah?
It's a polynomial, so it has to be.
That's right. Are you guys connecting this logic here? This is really good. We're getting it from different people, but it's all really well connected. So let's say that, right? So let's say this. F of x, let's go with that. F of x is continuous because it's a polynomial. It's a good place to start. And we know from our discussion yesterday that polynomials are always continuous, and so that's why that word was chosen. Okay, so f of x is continuous because it's polynomial. I'll use the little therefore thing and connect this with where Zach was going. Therefore, the IVT applies. Or no, somebody else said IVT. Zach was talking about the above 2, below 2 thing, right? Yeah, okay. So that's kind of like we've met the conditions, right? We've said, hey, continuity, we can use the IVT. It's continuous because it's polynomial. But now we got to start discussing Zach's ideas. So we want to find y values that are either above or below 2 and kind of discern the pattern. And from that, we should be able to tell the minimum number of times that f of x equals 2. So, I don't know. What do you see up there in the table that might start giving us a hint about that pattern of behavior that Zach was referring to? Hello. You want to bring any points out of the table? Zach, you brought up the idea, so let's let somebody else contribute. Let's let somebody else connect the table to what you said. You see anything like that, Colin?
Yes, value Q has a y value of 0, which is below 2.
So I'm going to write it like this. F of 2 equals 0, which is less than 2. So what Colin has brought out here, of course, is that we found a y value that's less than 2. So that's part of it. Now we want to find a y value that has what relation to 2?
More than 2.
More than 2. Do you see anything like that? F of 4, yeah. So f of 4 equals 3, which is greater than 2. So connecting the continuity that was mentioned earlier, the IVT concept, with those two statements that were brought right out of the table, that's one time right there, isn't it? Now maybe there are other times. So at f of 4, we're above 2, wouldn't we have to drop that back down below 2 to get another instance of f of x equaling 2? So do you see any other places where f drops below 2? 9. So we could say f of 9 equals 1, which of course is less than 2. So there's yet another instance. So we're up to a total of 2 times minimum. Maybe there's more. Are there any indications that y goes above 2 again? 13, yeah. So f of 13 equals 7, which is bigger than 2. So there is yet another time. Is there any indication now that we're above 2 that we're going to go back below 2? There's not. So how many times does that data indicate? 3 times. Yep. So we'd get 1 time here, 2nd time there, a 3rd time there. So we start off below 2, then we go above. So there's 1, then we go below. There's a 2nd one, then we go back above. There's your 3rd time. So your conclusion then would be minimum of 3 times. And based on the fact that we met the conditions, use the data in the table, we can say that 3 times would be the minimum that we would actually find f of x equaling 2. Could there be more? Of course there could, right? Between any one of those data points, y could swing back and forth across 2 any number of times. But 3 would be the minimum. That make sense? Isn't that totally different than some of the questions you get asked in pre-calc? It's like, hey, find the answer here. We're not really interested in what the answer is because I don't think we can find it. But we certainly can tell how many answers we might get at a minimum. You follow? Yeah. Okay, fair enough. Any questions before we finish this up?
Would it be wrong to say greater than or equal
To
to
3, you mean?
No, for like when you're writing it out.
Oh, or equal to 2? Well, that's technically not true because 0 is not. Well, yeah, 0 is less than or equal to 2, I guess. Yeah, Yeah, it's definitely not necessary. I'll have to think about that. I don't see why you would do that, but it wouldn't be a false statement. But it also might kind of mess with the concept of the IVT of being below than above, right? It could cause some confusion. I don't know. I'll think about that. That's a good question. All right. Okay, we're good. Take a look at C, please. C says 3 values of g of x are shown below. What is the minimum number of x-intercepts for g of x? Down below you can kind of see the little paragraph briefly goes over the thing that we kind of talked about at the start about, hey, the IVT is not about finding what the answer is necessarily. It's about finding, does the answer exist? And if so, how many could there be? That kind of thing. So we have a couple of others we'll talk about this year, but the IVT is the one we're doing right now.
I'm not talking about the answer. Are we assuming that there's only one y each x?
Oh, that it's a function? Yeah. Yeah, I would say so. Okay, so we're discussing, thinking about C. It really is a similar question to B, right? It's wanting to know the minimum number of solutions, minimum number of answers, essentially. So very similar to C, or to B. All right. So I don't often do this, but let's just do it like this. You guys all have an idea of an answer?
Yes.
Okay, so on the count of 3, I want you to just shout your answer out, all right? 1, 2, 3.
0.
I heard 0 and I heard 1. Did I mishear anybody? Did anybody say something different? 0 or 1. Okay, so you guys all said 1, right? You said 0, and you guys said 1. I heard some other ones. I'll let you defend.
I understand his point, but I don't know.
Okay. Okay, so let's hear. You guys said 1 because
We assumed that it was continuous.
So essentially, you trace the graph, right? You said something like that. So there it is. One time, okay. And Cole, you said 0, and others agreed with you, and you say 0 because...
Because we don't know it's continuous.
So 0 because we don't know it's continuous. Okay. Anybody else have a contribution? Or we all fall into one of those two camps, either 1 or 0? I think I would probably say this. We don't know. Why don't we know?
Because we don't know what the fact
Regarding
the continuity.
continuity. Yeah, we don't know the information about continuity. So, if you did say 1, I mean, Noah, you said it well. You're like, well, we were kind of assuming it was continuous. And if it is continuous, then 1 would definitely be the logical answer, no doubt. 0 kind of makes sense, right? Because 0 would, you can't have negative numbers of x-intercepts, right? And so 0 really does kind of make sense. But in the most general answer, I would say we simply can't draw a conclusion because we don't know about the continuity. You can all see, of course, that if I were to draw this graph with a lack of continuity, I could avoid the x-axis altogether, couldn't I? I could draw it like that, and so 0 could be the number of x-intercepts. But we simply don't know if it's a situation like that, or if it's a nice continuous graph, or, whatever. 1 or 0 would be the two logical answers, but I think we have to go with either 0 or I don't know because of the lack of information about continuity. All right, how are we sitting? Are we sitting pretty? Is this good? Yes? Okay, fantastic. Let's see here. Let's check and see where we are. I think we are at the end, are we not? Okay. Excellent. Okay, let's take a look here at 1.5. That's the final section in chapter 1 or chapter 1 notes here. Hey, I do want to mention this. This is always something that comes up. The quiz that you guys have coming up on Thursday, right? Thursday? Or tomorrow. Tomorrow. Man, I always mix these things up. Because we have our third meeting tomorrow. Yeah. So the quiz we have coming up tomorrow, this 1.5 thing is not on it at all. And if we do get into chapter 2 a little bit, that's not on there either. We're going to just kind of keep moving along. We're not going to rush or anything, but we'll keep plodding along. But just know that the quiz material just stopped. And we'll do another quiz later on this stuff.
So if there was to be a function that has close approaching like infinity for the quiz tomorrow, we just say like the limit doesn't exist.
Well, I would take either answer,
Okay.
infinity or d. To me, good math is good math. And so, if you if you remember that, or maybe you read ahead in the book and it's correct, I'm not going to be like, oh, that didn't come from this section, I'm sorry.
Okay.
Unless I've specified you need to use this method,
Okay.
then anything that's mathematically correct is valid.
Okay.
At the reading, it's amazing. I've been doing this long enough. Infinite limit's a limit in which f of x increases or decreases without bound. It is called an infinite limit. That's the term here. And no, that would be, I guess that would be one of those definitions you might be concerned about. I'm not going to ask you to, memorize that word for word, but I would want you to know what it is and what it means. So the notation here is limit as x goes to c of f of x equals either positive or negative infinity. Let's talk about what it does not mean. Maybe you remember this from the summer packet. It does not mean that the point c comma infinity or c comma negative infinity is on the graph. Right? You can't have a point where the y-coordinate is infinity because infinity is most certainly not a number. It's more of a philosophical concept than it is an actual number. And so you don't have a point on the graph like that. What it does mean is that the behavior of the graph, just like we talked about with limits, the behavior of the graph is boundless. In other words, it's going up forever or dropping down forever. Therefore, the y values are headed towards an infinite concept or towards a negative infinite concept. But it certainly does not mean that there's a point on the graph, c comma plus or minus infinity. You could certainly, you could do this analytically, but often the graph is the best way to do this. And say a picture is worth 1,000 words. I agree with that in this case. So take a look here at our graphs down below, determining these limits from a graph. Could look something like this. On the left, if you were to have a question in regard to that, maybe it would say limit as x goes to 1 of f of x. So you can see some things from the graph right there. So from the left of 1, what is the graph doing? Doing what? Increasing without bound. It's going up, 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 right? From the right, the graph is doing the same thing, isn't it? And so from the left and the right, we're seeing an increase without bound. And so this gets to Zach's question kind of earlier. In the past, we might have put DNE, and that's justified because, increasing without bound or decreasing without bound is not a number, right? We can't define that on the number line. And so that's really justified. But now we're going to try to be a little more descriptive of it. And I am just struggling this morning. And put positive infinity. Because although positive infinity is not a number, that does describe the pattern of behavior a little bit better than just DNE. Follow okay? The other one's a little more interesting. And if we were to ask this question, let's go 3 questions here. If I were to say A, limit as x approaches 1 from the left of f of x, what would you say?
Infinity.
As you approach from the left, it's increasing without bound, so infinity, just like we looked at a second ago. If we said question B, limit as x goes to 1 from the right of f of x, what would you say there?
Negative infinity.
Negative infinity, because it's decreasing without bound. Then if question C was limit as x goes to 1 of f of x, what would you respond to that?
Doesn't exist.
And your reasoning would be?
Right hand and left hand limits.
Like radically different behavior, right? The behaviors could not possibly be any more different than one going to positive infinity, the other one headed towards negative infinity. And so I think that's one of the reasons that it's a good idea to answer this one over here with infinity. Because if you answered that one with DNE, doesn't that sort of imply that you have the same kind of thing as the other DNE? But they're totally different, right? The one on the left, they're both going up without bound. The one on the right, they're going opposite directions without bound. So they're completely different situations. So I think it's better to use the infinity notation in these cases. All right, so do you have any questions? Catherine.
On the quiz, will you want us to justify when it does not exist, such in that case? Listing.
Good question. Yeah, I mean, it could. I think it could go either way, right? So, if I could see a graph like that, a question like those, showing up in a multiple choice. In which case, you're just like done, right? But I can also see it being part of a discussion, right? Where you're like, hey, discuss why this limit doesn't exist.
Okay.
And so then you're going to be like, oh, well, it doesn't exist because of blah, blah, blah. And you have to explain yourself a little bit. And, you could use some of those one-sided limits to help with that. So it could go either way, I guess. Yeah, good question. All right. Any others? All right, we are cruising along. I throw this in here. Vertical asymptotes. It was funny. After the AP test comes out, they send you analysis of your student scores and tell you where your students were strong and where they were weak, things to improve on, stuff like that, right? That's kind of useful information. And so like 3 years ago, it said like the weakest point of my students was identifying asymptotes. And so I was just like, really? Okay, so I threw it in the notes. You probably know how to do this already, so please don't be insulted. It's not intended to be an insult. I was surprised to see that. So let's at least talk about this. Finding vertical asymptotes. What is something that could cause a vertical asymptote? A zero where? Yep, a zero in the denominator. That's not universally true, of course, because sometimes a zero in the denominator causes a hole, right? The removable discontinuity. But in some cases, that zero in the denominator, there we go, causes vertical asymptotes. So you take a look at example like number 1. What's the zero for the denominator?
-1.
-1. So then you look at that carefully and ask yourself, well, is something possibly going to cancel out with that factor that would turn it into just a hole, or is it really a vertical asymptote? It is, right? It is a vertical asymptote. So x equals -1 is a vertical asymptote. So again, not intended to be an insult. I know that you probably know this already. I just feel like probably should mention it based on the feedback that I got. Okay, and then finally, number 2. As you guys mentioned earlier, zeros in the denominator are likely candidates for vertical asymptote places. So what are the zeros of the denominator? 3 and negative 3, right? So we look carefully at that and we ask ourselves, well, at that plus minus 3, could we get a cancellation of a factor with the top that would cause it to just be a whole, or are those really truly vertical asymptotes? They are, aren't they? Yeah, so plus minus 3 would be the vertical asymptotes. All you're really doing, of course, is you're setting the denominator equal to 0, and you're solving. You get x equals plus minus 3. No matter what method you use, you should end up with that. So that's kind of it. Let's take a look at our final couple of questions in 1.5. Get your calculators out if you haven't already done so. So, I think... Oh, there's a little typo on this. Sorry. So 1 is fine. Number 2, gosh, I think I've had this typo for like 3 years running. Hang on just a second. On number 2, will you guys please change x squared plus 16 to x squared minus 16? If you can make that change, will you please do numbers 1 and 2, but not 3? Use your calculator to help you out. Johnny, you had a question, right?
Yeah, number 2, the last one, would that be a slant asymptote, or
Let's see here.
Same thing right here.
Okay, so I did my best to sketch those graphs up there for you. Hopefully you saw the same kind of things on your calculators. So if we do take a look at number 1, Eliza, what would you say as we approach 1 from the right, what would you say we would get there? So she says negative infinity. So 1 from the right. So that would be something like that. So you can see decreasing without bound. Excellent. Does that make sense to you guys? Any questions? Take a look then at number 2. This says x approaches 4 from the left. Nick, what did you say to that one? You said infinity? So we approach 4 from the left. Negative infinity, probably?
Yeah.
There's a lot of positive and negative infinities going on with that graph, right?
Yeah.
Certainly multiple choices there, but I would say probably negative infinity because we're going from the left. So whether you go from the left or from the right is going to make a lot of difference. You can see how a question could be fashioned to get either infinity or negative infinity as answers from either one of those graphs, right? Really could. We could ask a slightly different question and get positive infinity. Okay, so are we good? We happy with that part? Okay, there is another typo on 3. Normally there's not any typos in these, but there's a typo in number 3. Let's make it interesting. Let's go with, as x approaches 0. Again, let's use a graph. So I'm just going to erase this and say x arrow 0 instead of 3. So look at your calculator, give that a shot. I will attempt to sketch the graph up here too. Are you allowed to cross through a horizontal asymptote? Is a graph allowed to cross a horizontal asymptote? Yeah, on the long-term behavior, no. But don't we see that happening right here? Do you guys notice? The horizontal asymptote appears to be the x-axis, right? Yet we cross through it at 2. You can see it on your graph. How is that possible? Well, horizontal asymptotes really are only describing long-term behavior on the far right end or the far left end. Can you cross vertical asymptotes, though? Why not?
Because that means you would have multiple answers.
Well, what does crossing a vertical asymptote indicate?
0 in the denominator.
Division by 0, which we can't do. So you can never cross a vertical, but you could cross a horizontal. So, okay, cool. All right, so as x approaches 0, that particular graph approaches negative infinity. Catherine, you had a question?
Yeah, can you explain again why you can cross horizontal asymptotes?
Simply because a horizontal asymptote is not the same as a vertical asymptote. It's like
Right.
where it comes from. So vertical describes division by 0, which you can't do. Horizontal describes only like what we call long-term behavior. As x gets really, really huge, what pattern of behavior do we see?
Okay.
And so you can have x-intercepts all through there if you have an x-axis that's a horizontal asymptote. But as you get to the far right edge of the graph, you'll see it kind of cozying up to the x-axis
Okay.
and not crossing it. So, but you can cross it at other places, where you actually do have zeros.
Okay.
All right. That's the last one. Do you have any questions? Go ahead,
Why
Noah.
was this one not with me, but the one on the first page was?
So why is this not a DNE?
This one was as X versus 1.
Sure, yeah, good question. So you notice on that one right there, the graph did this and this, right? So as you approached, was it 1? Yeah. So as you approach 1, from the left, we're approaching positive infinity. From the right, and the derivative can take on all sorts of shapes and forms and types, but this would be a real basic definition of kind of that slope of the tangent line, aka the derivative. Okay, so let's take a look here at a little bit more. We're doing really good. Have you guys seen it presented like that? Did you see the H's in pre-calc instead of the delta X's? So that's a really common way. I think the AP test almost always uses H's. I'll typically use H's as well. So the slope of the tangent line, a little notational thing here. This is one notation for the slope of the tangent line, often referred to as the derivative. The derivative can describe a lot of stuff. The derivative does not have to be y in terms of x. It could be h in terms of t, or c in terms of v, or any one of another, like all kinds of different combinations of letters and meanings of variables and things. But the slope of the tangent line will always be change in y over change in x, or the dy over dx. Okay, so then just a terminology thing. If you are going to do the derivative or find the derivative, we call that differentiation. So the most commonly misused word there is I'm going to derive it, right? And so this is just a point of terminology. Like if you say that, it's not like I'm going to go, oh, Nick said derive -5. I'm not going to go there, right? But I just want you to know if you end up with, taking some calculus class later on in college, the term is differentiation. That's like the verb form of what we're doing. It's not derive. Fair enough? Okay, cool. So let's go through a couple more things here. I'm so excited. We're making progress. This is lovely. You guys remember all this stuff? Kind of. I hope your pre-calc teachers covered this. We'll see how this times out. We'll see how it goes. So the derivative is, we could describe this in a number of ways. The slope of the tangent line. That's just what we were focusing on. So slope of the tangent line. We could also call the derivative the slope at blank point. 1. Yeah, 1 point or one specific point. And then Jackson has said this once or twice here today, I think. The blank rate of change? Instantaneous. Yeah, so that's more of a kind of an application thought there. Instantaneous rate of change. Let's try that again. Instantaneous. There we go. So those are all some real basic descriptions. And believe it or not, there are going to be plenty of times this year when you're going to want to be able to use those words to describe something. For instance, let me give you an example here. I'll just do this off to the side. I wasn't really planning on doing this, but I think this is worthwhile. So if I told you, we've talked about, you guys talked about notations for the, let's talk about notations and we'll talk about what I want to talk about. Let's do this first. So notations for the derivative look like this. Did you guys all use Newton's notation? The one it's like f prime of x? So this is kind of a variation on what Newton used. Originally Newton used, I think it would have been called f dot. Oops. With a little, come on, work. With a little dot above the f. And that little dot kind of migrated down eventually and became a prime for whatever reason. So, but that we do consider that to be Newton's notation for the derivative. F prime, that could of course be y prime. It could be g prime. Could be lots of stuff. So I'm kind of hinting at this, but Newton was one of the early developers of calculus. Maybe you remember that. But there was another guy. Newton was from England. This other guy was from Germany. Have you ever heard of him? He's less famous, but he did some really, really awesome stuff. Ever heard of him? So this is all Newton stuff. The other guy was named that. That was his last name. Leibniz, I think, or Leibniz, I've heard it pronounced that way as well. So he came up with the other notation we use a lot, dy dx. This can be extended to be all kinds of things. It could be dv dt. And we do say dy dx. We don't say dy over dx, even though that's really what it is. We just say dy dx because I guess we all agree that that's kind of what it means. But he uses all the little d's. And if you think about it, since the derivative is the slope of the tangent line, we all saw this a long time ago, delta y over delta x. Doesn't Leibniz's notation have kind of a beautiful symmetry? Because delta starts with the letter d, and that little d is supposed to represent like a little itty-bitty change in y, or a little itty-bitty change in x, whereas the delta y was like a big change in y, or a big change in x. So there's a lot of cool meaning in that. So let me talk to you real quick about what some of the meanings of these things could be, and what you might be expected to do. So let's say, I don't know, b of t. Let's say that b of t represented the number of boys in the room. Number of boys in the room, b of t. Fair enough? Some function describes the number of boys that are in the room. But let's say that somebody took the derivative of that, and they had b prime of t, and let's say they specifically figured out b prime of 2. Now, from an application standpoint, we said that the derivative is the instantaneous rate of change. So I can see a question like this on some quiz or test in the future for sure. I might give you b prime of 2 and give you a brief description of what b of t stands for, but then the question might not be find b prime of 2, it might be b prime of 2 equals, I might tell you this, b prime of 2 equals 10, and my question to you might be, what does that mean? Right? And so your response would be something like, that's the rate of change of boys coming in or leaving the room, whatever it is, at time t equals 2 minutes, or whatever it might be. So that's why you want to know, okay, the slope of the tangent line, the instantaneous rate of change. You want to know those meanings, right? Because there are going to be questions where it's like, I'll give you the expression, I'll give you the answer and say, neat, what does it mean though? And you got to figure out what that thing actually means. Does that make sense? So if you know what you're talking about, that's actually a pretty darn easy question. If you don't know the meaning of it, it becomes very difficult. But I'm forewarning you, we'll work on it. We'll practice it a lot too. So hopefully that'll end up being an easy one for you. Okay. Woo! We covered a lot of ground there. Appreciate your hard work. I will look forward to seeing you tomorrow for your very first quiz.
Will you be in here?
Have a wonderful day. Yep, should be.
Thank you.
You are very welcome.